So for acid chlorides of R, and the carbonyl attached to a chlorine, and the reason why you see a lot of these guys when you want to react really anything with a terminal carbonyl on it is because of the inductive effect of the electronegative chlorine. Okay, if this is electron withdrawing because it's in the top right corner of the periodic table because of electronegativity, then what you're going to get is kind of like a double whammy effect, in a sense that you have electronegative oxygen, which is pulling the electron density away from the carbon, making it more reactive, as well as the chlorine. So now, where before you had this delta plus, this delta minus, just based on the fact that you have C double bond O, right? Put a delta plus, delta minus. Now it's really going to be delta plus. So maybe this, circle that there. Right there. But this plus here is going to be really, really plus now. Thereby making that carbon more electrophilic. So it's going to be more attracted. It's going to be more attracted to a nucleophile. Okay. So yeah, carbonyls. Let's draw a different color here. Are very common in organic chemistry because it makes carbon, which is not really so reactive, right? Because you have a electronegative atom attached to the carbon, drawing the electron density away, and again, it's making the carbon, which is really, since it's a group 4, and it's kind of right in the middle of the periodic table, if you're thinking of the octet rule, which means that, of course, atoms like to have 8 valence electrons in their outer shell. It's kind of drawing electron density away from that nice neutral carbon to make it to put a charge on it, or a small charge on it, partial charge, which is what that delta plus means. Small Greek letter D, delta means change, so small change, right? So acid chlorides, they have a pretty unique property in the sense that this chlorine, again, makes this carbon even more electrophilic, or even more delta plus than it normally would be if there was something else attached to it. All right, so these guys are pretty common in terms of, well, let's say if you want to react water with this acid chloride. What's going to happen is, I'll draw the water like this. Just draw it again right over here, just to show the mechanism. And what happens is, even though we have a weak nucleophile here, because the acid chloride is creating such a strongly or strong electrophile here, the weak base water can behave as a nucleophile attack the carbon, and it's going to push the electrons up to form something like this. So you have, back to the right color here, O minus, Cl, and let's see what happened to the water. Well, the water actually had to throw one of its electrons over here to make this bond, so it's missing an electron. So it's going to be plus. All right. And this compound here is pretty unstable, so what will then happen is this negative charge is going to come down, kick off this weak electrophile or leaving group. Actually, weak nucleophile, which makes a good leaving group, is chlorine. And have, let's see, double bond now here. Water. Let's make it all one color. With the positive charge. And assuming there's a lot of water around, water which is behaving as a nucleophile here can also be a weak base to plug off a proton. And once it plugs that proton off, what you wind up with is carboxylic acid, starting from acid chloride again, which is a really good starting material considering the fact that it makes this carbon more electrophilic because of the electronegative chlorine due to the inductive effect.